So with that, I want to quickly introduce Erik. Erik and I have known each other since 2015, where I was a research intern at IBM Research in New York. Back then, he was a research staff member working on API Harmony. So he's always been within this API space. He has now transitioned to a role at IBM, where he works on GraphQL. And I'm very excited to hear what Erik is going to talk about today. So Erik, take it away.
Yes, hello everyone. Jürgen, thank you for the introduction. I'm going to talk about client-server communication with GraphQL today. I'm super excited about that because GraphQL is a topic that's really near and dear to me. And as Jürgen said, I do work for IBM, but I just want to give a very small disclaimer up front that today I'm speaking as Erik Wittan, the private person. So what I'm about to say does not necessarily reflect the position of my employer, IBM. So as Jürgen does it, I want to give a small overview of the learning goals for today. I basically want to tell you what GraphQL actually is and what led to its creation in the first place. I then want to go a little bit into the details of how GraphQL works, and then contrast GraphQL with some other API models and basically talk about some of the benefits versus challenges that you encounter when using GraphQL. So let's start with some background and overview. And let's start with the origin history of GraphQL. And GraphQL was originally invented at Facebook. And the situation that Facebook faced was in 2011, there was this big technological transition within Facebook. So Facebook had, after it had been founded, has always been this website basically. And in 2011, there was industry-wide this major shift to mobile, right? The iPhone had been introduced in 2007, and in 2011, more and more people were using smartphones to access services like Facebook. And Facebook at that point didn't really have a great mobile strategy. They were still just serving their website basically. And if you were to use Facebook on a smartphone, you would basically just get a mobile version of their website. Even if you were to download the Facebook app from an app store, right, it was basically just a thin wrapper around Facebook's website. And in 2011, there were a lot of technological constraints around using websites. So one of the things was that there was this lag that was introduced when you clicked the link in a browser of a few hundred milliseconds. And it was introduced so that the browser could differentiate between like a scrolling input and an actual click. So that made some browser applications feel really sluggish, right? Because you clicked and then you had to wait a little bit before something actually happened. You also had very limited access to the hardware on your device, right? It was very difficult to access the camera from a browser app. And so there were all these issues with web applications and web apps. And so Facebook basically made this major transition and they said, look, we're gonna build native clients on all these different platforms. We're gonna build a client for iOS on iPhone, we're going to build Android clients, we're going to build a client for iPad, and so on and so forth. And what that led to was that they suddenly, instead of having just a single HTML website, right, they basically had these diverse clients, and they had to shift from rendering HTML on the server and sending it to a browser to providing some other mechanism for the clients to access the Facebook data. And what you typically do in a case like that is you build some kind of networked API, right? An API is an application programming interface. And I think you've already learned in Jürgen's lecture about a common style, the REST style of building APIs, right? And so with the increasing number of clients, what happened at Facebook was that there was an increasing number of API endpoints, right? Different clients had different requirements for different pieces of data. And whenever new clients came to the picture, Facebook backend and server engineers basically added new endpoints that were specific for that client, right? And at some point, you end up with having a very large amount of API endpoints that all do different things. And that can become really problematic because you have to maintain all these API endpoints, right? You have suddenly a very complex system. And you cannot just simply deprecate them because imagine you roll out a client application on some device and people may still be using that device even if the version of the client evolves over time, right? It may be that your customers don't actually update that client version And so you really have to maintain these old endpoints, which Facebook in retrospect actually termed ad hoc endpoints. And so the predominant API model at the time, right, and which is still common today, the REST model, it has this concept where basically the developer of the server, the backend developer, decides what are the endpoints, right? And if a client has requirements that don't meet the existing endpoints, then they basically have to talk to the backend engineers, and the backend engineers have to figure out if they can add an additional endpoint. And so there's also a lot of friction, right, in the communication between front-end and back-end engineers. So that's a big issue that Facebook started to face in the beginning of 2012. And interestingly, Facebook was not the only company for that with that problem, right? Others included SoundCloud at the time and Netflix. So basically, companies that had different evolving clients, right? They all faced similar problems. And actually, at Netflix, even a technology similar to GraphQL was developed at the time, but it didn't gain as much momentum as GraphQL did. So in order to address this problem with all these endpoints that you have to evolve, right, as you have more and more evolving clients, Facebook introduced GraphQL. So what is GraphQL, right? How does it work? To give you an overview, right, with GraphQL, the provider define the data types that they want to offer on their server at design time. So here, for example, you see some definitions for some data. You see that there's a type query, which allows you to query for a field called me, which returns a user. And then we have the definition of the type user, which states that a user has a name of type string and an age of type integer, right? So at runtime, what clients can then do is they can basically write queries, and they can ask for some of the data that is described by the server. So in this case, here you see there's a query which asks for the field me, which returns a user, right? And then the query asks for the name. And sending a query like that to the server can execute it and produce a response. And the response that you see here in JSON format, right, pretty much is in line structurally with the query itself, right? So what's being returned is some data, the me field, which returns a user object with the name Eric. And you note, right, that in this query, the query didn't ask for the age, right? And so the response doesn't include this field because the client was not interested in this. But later, right, if the requirements of the client change, they may adapt their query and ask for the age in addition to the name, and then the response would also reflect the age. So the fundamental difference here between GraphQL and previous API models is that GraphQL really shifts the control over what data to fetch from the backend engineers to the front-end engineers, right? Because the front-end engineers define these queries, and they have control of what data they want to have a server return. So that's a pretty drastic shift. And I want to give a small demo to really drive this point home. So over the weekend, I have built this application, this demo application, which uses the GitHub API to fetch some pull requests and the first comments on each pull request for a given repository. So you have this input field here where you can input the name of some GitHub repository identified by the owner and then the name. So here, for example, Facebook React, right, is a popular front-end framework. And if you hit load, then you see there's some data being loaded. And once that finish, we see the result of that, which takes quite a long time. Maybe GitHub is having some issues. But I hope it's going to finish. There we go. Took a really long time. I'm sorry for that. So now that the data has been loaded, what we see is, we have this repository, Facebook React, a description, right, a declarative, efficient, and flexible JavaScript library for building user interfaces. And then you have a list of the latest pull requests that were created by some users with some title and a description. And you have a few comments per pull request being rendered here, right? So you have a bunch of these things. So let's maybe look at how this app works. So this app structurally is very similar to the ones that you learned about in your last lecture, when you learned about writing clients, writing front ends. This is a single page app, so it has a single index HTML, which basically doesn't contain anything except loading some data, some JavaScript. And the JavaScript here is using React, which is a front-end framework similar to Vue that you learned about, and it's basically rendering an application. And the application has some global data basically, and close this down for a second, and it renders the content of this application based on the state here. So in the beginning, the state is welcome. That's when we just loaded the app. It says welcome here, and some text. And on top here, it also has a form, right? A form component, which basically defines some input that I can put something in. And then if I enter something in here, right, it calls this fetch data function, which is then responsible to fetch the corresponding data for a repository. So first thing that it does is it sets the state to loading. So this is what you see, for you just saw it for a very long time, right? When I hit the button, it goes to loading. And it then passes the input of the form, right? And this is very similar to the recipes app that Jürgen live coded for you. It basically just takes the input string, it splits it by the slash in the middle, and then basically extracts the owner and the name of the repository. And then it basically does the main work. It goes into this fetch REST function, which uses the REST API of GitHub to fetch the data. So how does that work? Well, there's actually, in order to fetch the data that we want for this application, there's a number of requests that need to be made. First of all, we want to fetch some data on the repository itself, right? Using this URL where we include the owner and the name. And we do this before we do anything else because we want to make sure that this repository actually exists. So if maybe a repository didn't exist, then we can actually throw an error. So if we put something senseless in here, right, there's probably no repository with that name by Facebook, and so we can render an error. But if it did fetch the data, then we can actually load the list of the latest pull requests, and we are going with 10 pull requests in this case. And once we have loaded the list of pull requests for each one of them, we can basically use this helper function to fetch the comments. So we fetch comments for each one of these pull requests. And as you can already imagine, let me go to this app again and inspect. There's actually a lot of network requests going on to fetch this, to fetch the data here. Again, I'm not 100% sure why it takes such a long time. I don't know, maybe something's really wrong with GitHub. But so this is the initial request, right? We are fetching some data on the repository here. We see the response. There's a bunch of data coming back. And then the next request is we got the 10 latest pull requests for that repository. And then we basically, for each one of these pull requests, we're fetching up to 3 comments, right? And you can see that this actually took a very long time. And overall, we performed, or we're in the process of performing 12 requests and transmitting, in this case, 35.7 kilobytes compressed to fetch this data. Now, if GitHub's API was a little bit faster today, that's actually not very efficient, right? Why do we have to perform 12 requests, right? And fetch all of this data. And if you look at it, right, there's a bunch of data in here that is not really rendered on the page anywhere, right? There's like a bunch of URLs that point to other places in the GitHub API that we are not really interested in. So we are really overfetching here, and we're doing a lot of requests to get this data. So the API that we are using, right, that's GitHub's REST API version 3.3, which we're currently using. And there's a lot of documentation on how to use it. And the way that I used it, I basically just looked through this documentation and figured out what are all the requests that I need to make to get the data that I wanted. But fortunately, GitHub also offers API version 4, and that's a GraphQL API, right? And they have some documentation for that as well. And they also have this cool feature called the Explorer, which is basically a tool that you can use in order to interact with the GitHub API from the browser. right? And you see here this, this tool that's embedded in this page is called GraphQL. And GraphQL is a very common GraphQL client that developers can use to familiarize with the GraphQL API. And you see it comes preloaded actually with the query on the left-hand side here. And that query looks very similar to what I've shown you on the slides, right? Here we are asking for the viewer, and that's actually the logged in user. And then for the login name of that user. And if I hit this button here, I will actually execute this query. I will send it to GitHub server, and it's going to give me back the response, right? And the response is Eric Wittham. That's my handle because I'm currently logged into GitHub. So thinking back of the application that we just wanted to build, let's see if we can use GraphQL to fetch the data that we need in order to render that application, right? And so I can start writing a query here. And the first thing that we want to fetch actually is a repository, right? And we don't want just any repository, but we want a repository. In this case, we said Facebook, and the name was React. And then we want to fetch some fields for that repository. For one, we want to fetch the name. We want to get the description maybe. And then we were interested in the pull requests for that repository, right? And so I can start writing pull requests, and I can state which pull request I want, and I want the last 10 pull requests. And then per pull request, we want the title, the description. Doesn't that exist? Oh, maybe not. Maybe the body. Yeah, the text basically of the pull request. And we want to know when it was created. And then per pull request, we actually also want to get the latest comments, right? So we can say, actually not the latest comment, but the first comments that were created. So the first 3 comments per pull request. And then for these comments, right, we are interested again in the, oh, actually we want the author as well. We want to see who created it. And the same for the pull request, right? We want to see who the author is, who created that thing. Oh, that's enough for the author. What else do we, oh, sorry. What else do we want for the pull request? We want the body maybe. And yeah, that looks good. Let me prettify this. I messed this up a little bit. So we have this query here, and now let's execute it. And ta-da, we get the data back that looks pretty much in line with the query that we made. And we actually now caught all the data that we wanted to fetch in a single request. So we could now use this query instead of the logic that I've shown you for the previous REST API to fetch this data. And in my example app, in order to do that, I can just comment out the fetch using the REST API, and I can comment in the fetch using the GraphQL API. And you can see in here, right, I basically have a query string that looks pretty much like the query that I've just built up here. We make a single request to return that data. So if we go back to this application, this has actually restarted, right? Because I have a dev script running so that when I saved the changes here in the app file, it actually restarted this. And so let's try to fetch the same thing again, right? Let's try to get some data for Facebook React. And we are running this request. It's still super slow for some reason, but we now see that the request here actually just went to the route GraphQL. And we see that it's finished. It's a single request, and we see that the application now renders the exact same content as before, but we did only 1 request instead of 12 requests, and we transmitted only 11.2 kilobytes because we actually only asked for exactly the data that we want to render here, right? So there's no superfluous data being returned. And this is all possible because with GraphQL, right, as the engineer who's actually writing this application, the front-end engineer, you basically have much more control over what data you want the backend to return. So if you think of a mobile application, right, doing 1 instead of 12 requests and fetching less data can actually be super important for performance. Back to the slides. So what is GraphQL, right? So GraphQL is this technology that Facebook invented in 2012, and they had these problems with all these API endpoints. And it's basically a query language for building networked APIs. And it's also a runtime that basically defines how such queries are fulfilled by servers that offer a GraphQL API. The way that GraphQL is made available is in the form of a specification, which basically defines exactly how this query language is supposed to look like and how queries are supposed to be executed, as well as a reference implementation in JavaScript that people can use to build their servers on. There's obviously implementations for GraphQL in all kinds of programming languages, but the reference implementation is in JavaScript. So, and to remind once more, or to give once more an overview of how GraphQL works at runtime, right? A GraphQL client like GraphQL, like the one that we've seen also on the GitHub page, right? What it typically starts with is it performs a special request, which is called an introspection request. And the introspection request asks the GraphQL server to basically tell the client what are all the different data types that the server has available and what are the operations that you can run on that data, right? So it's basically asking the server to self-identify. And with that information in hand, the client can then start to form queries and can actually make sure from the introspection data that these queries are valid and in line with the capabilities that the server has to offer. And once a query is formed, you can send that query to the server, and the server can then execute it. And to do so, it may speak to arbitrary other backend components. It can speak to databases, it can speak to external APIs of any nature, or it can speak to mainframes or what have you to basically produce the data that the query asks for. And once it did produce the data, it sends it back as a response, and it gets then returned to the client who can then do something with it. So that's basically the overview of what GraphQL is. So the history, right? I already told you it was developed originally by Facebook to deal with their issues. In September 2015, they decided to open source it. And then it took basically 1 year for GraphQL to become a little bit more stable, also based on some input from the community. So it moved from being a technical preview to a working draft. And then in November of 2018, there was an announcement of the GraphQL Foundation being created. And the GraphQL Foundation is part of the Linux Foundation. And what it basically does is it shifts the ownership from GraphQL away from just being owned by Facebook to this foundation. And the foundation, you know, people from all kinds of organizations can participate in the foundation. So there is now a much broader set of people who collectively work on evolving GraphQL. And the way that that actually works is there's meetings once a month where people can make proposals for changes on GraphQL, and these proposals are then discussed and go through a process of different stages until they may or may not eventually get adopted by the official GraphQL specification. So much for the overview of GraphQL. I want to now shift and talk a little bit more in detail about the language, the query language, and the runtime that is executing such queries. So the GraphQL language actually consists of two parts. There's the part where clients basically write queries, and there's the second part where providers basically use the GraphQL language to describe the type system of the server that they are building. So let's start with the queries, right? So what you see here on the page is a query that is kind of similar to the one that I've just created for the GitHub API, but it has a little bit more complex constructs, which are not all of the constructs that the GraphQL query language supports, but some important one of them. So I want to walk you through basically, right? So we're defining a query here, right? So this is the operation type. Query means that we want to fetch some data from the server. There's two other operation types in GraphQL. The one is mutation, which you would use if you want to create or update some data on the server. And the other one is subscriptions, where you basically subscribe to updates from the server. So the server can then basically push updates to the client. And this is often used when you want to build some kind of like real-time application, like a chat or something, where you want, when a new message comes in the chat, right, you want the server to basically push down this new message to all subscribed clients. We next have the operation name. So this query is named fetch GraphQL data. An operation name is important because a query document like this could actually contain multiple queries. And in the case where you have that, you need to identify which query you actually want to execute on the server. We then have variable definitions. So variable definitions basically allow you to provide separately from the query some values, some data, and they will basically get injected into the query during query execution. So we say here, for example, that we have a variable called details, which is of Boolean type. And the exclamation mark here basically states that this is a required Boolean type. So you cannot simply leave out the details variable value. You have to actually provide it, right? It's a non-null value. Next, we have these opening curly braces, and they close down here. And this is what's called a selection set, right? So a selection set, within a selection set, you can make selections for the things that you want to query in this case, right? And the first thing that we do here is we make a selection for a field. The field is called repository, right? And in order to identify the exact repository we're interested in, we have to provide two arguments, right? We have to provide the owner, we have to give a string for that, and the name, we have to give another string for that. And then within the repository, we have another selection set down here. And then again, we have selections within that selection set. This one here is called a fragment spread, right? A fragment spread has a name, repo details, and it must have a definition somewhere. And the definition is actually down here outside of the actual operation. So we have a definition of a fragment called repo details. And that fragment can be used on the type repository, which is the type that the field repository returns. And we can basically say that we want to fetch the name and the description of that repository. Now you see there's some interesting construct here with the name. There's actually an alias being used where we say we want the name to be contained in the response in the field repo name. So we can basically rename the field that contains this value. So this fragment is basically included in here, in the selection set. And the next thing that we see is next to it, we have a so-called directive. And a directive is basically allowing you to annotate parts of a GraphQL query. And in this case, the include directive basically specifies whether this fragment spread here should actually be considered during the query execution. And it will be considered in the case where the argument value for the if argument here is true. Now, the value of the if argument is actually a variable, right? That's a variable we defined up in the beginning here of this query, so which is a Boolean value, right? So if the value of the details variable happens to be true, then we're gonna include this fragment spread and just gonna fetch the name and the description for the repository. Then again, we have another field selection here for issue or pull request. We want to get the issue or pull request with the identifier number 10. And then down here, we have an inline fragment, right, which is a different type of fragment from the one that we used before, because it's defined inline, which has a type condition, right? So on the type issue. So that's interesting, right? Why do we have this type condition? Well, look at the field name. The field that we are operating in is called issue or pull request. So this field actually returns a union type, which at runtime could be either turn out to be an issue or it could turn out to be a pull request. And if you know GitHub a little bit, you know that kind of makes sense because if you open a few issues, let's say issues 1 to 5 in a GitHub repository, and then you create a pull request, the number of that pull request is going to be 6 because issues and pull requests share the same numbering. So if we ask for an issue or pull request with number 10, we don't actually know exactly, is it going to be an issue or it's going to be a pull request? And so this inline fragment basically states that if it is an issue, we're gonna want to know the when it was last updated, right? And if it is not an issue, then actually we don't select anything in here and we will just get an empty object being returned. So these are some of the concepts that you can use when you're writing GraphQL queries. You may already see that this is a pretty powerful language for writing queries. And if you're interested in more of that, you should look at the GraphQL specification, which really defines what are all the things that you can do with the GraphQL query language. So now let's shift to the other side of the medal, to the side of using the GraphQL language on the backend to describe the type system that is offered by a GraphQL server, right? So this is this part of the GraphQL language is also called the schema definition language, or short SDL. So we start from the top here by defining a GraphQL schema, right? This is a schema definition. And we define the root operation type. So the root operation type basically says that in this schema, we can perform query operations, and the type of query operations or the fields that we can query for, they are defined in a type called query. And that type is defined next. This is an object type definition, right, with the name query. And we say that there's a single field called users. So this is a field definition. We have a field with the name users. We have an argument definition. So this field, in order to use it, it requires you to provide a limit argument with an integer number as the value. And then it returns a type. And this square brackets means that it returns a list of, in this case, users, right? So if we ask for some users, let's say limit 5, we're going to get a list back of up to 5 user objects, which are defined down here. What we also have in this schema definition is a directive definition. We've seen a directive being used before in the query on the previous slide, and in this slide we see the definition of a directive in the schema definition language. So we have a directive which has the name uppercase, and we can basically specify where we can use this directive, where it's valid to use that directives. And in this case, you can basically use this directive to annotate field definitions within the schema definition language. So down here in the type user, you actually see that the field definition name, which returns a string, actually makes use of this uppercase directive. And this uppercase directive, right, I made it up, but you could imagine that it basically tells the GraphQL backend to always uppercase the name of the user in this case. Next, we have the definition of an enum type. So an enum type, that's similar to the way that enums work in many programming languages, right? It can basically take one of a fixed set of values. In this case, the status can be active or inactive. And we see down here in the definition of the type user that the user has a status, so the user can be active or inactive. Again, you can find more details about the schema definition language in the GraphQL specification at the link down here at the bottom of the slide. And I want to give 2 more notes. So first of all, as with the queries, right, the schema definition language actually contains much more concepts. There's different types that can be defined, like scalar types, abstract types, which I didn't cover in this overview. And the second point that I want to make is, if you are a backend developer and you want to build a GraphQL server, it doesn't suffice that you just define the data types, right? Because you still need also the logic for actually fetching or storing data. So the schema definition language is only one part of what you need to do if you want to actually implement a GraphQL server. The second thing that you typically need to do is you need to implement so-called resolver functions. So resolver functions are associated with field definitions, and they are responsible for producing the data that a field returns. So consider, for example, here this field query.users, right, which returns a list of users, right? We basically now need to write, if you want to implement a GraphQL server, a resolver function that, for example, fetches the list of users from some database. So this is required in addition to this schema definition language in order to actually implement a GraphQL server. So to get a better idea of that, I want to basically show you a little bit how a typical GraphQL server might work. And as an example, let's use a GraphQL server that is built on top of the HTTP protocol, right? GraphQL itself is actually agnostic to the transport protocol. So you could build a GraphQL server that does not use HTTP, that uses, for example, some kind of binary transmission protocol. But in practice, most GraphQL servers are actually built on top of HTTP. So we have an HTTP server, and what happens at runtime is that we get an HTTP request that contains the query, right? There's different ways in which this request could be sent. It could be a GET request, and the query could be encoded as a query parameter in the URL. It could also be a POST request where the query is encoded in a JSON object which seems to be the case for this request, right? The request contains some JSON object, a field query contains the actual query string. So in the GraphQL server, the first component that you may typically hit is some kind of GraphQL middleware. So the GraphQL middleware is basically implemented to be able to deal with GraphQL requests that come in via HTTP. The first thing that it does is it will try to extract the request parameter. So it will see, for example, is this a post request? If so, is the query contained in the query field in the payload of that request? And if actually that's not the case, right? If some weird message comes into this GraphQL middleware, then it can immediately actually return an error, right? But let's assume that there is indeed the GraphQL query contained in the response. It will then pass it on to a parser, and the parser will basically now take this query string and translate it into an abstract syntax tree, right? That's like an in-memory representation of this, a structured representation of this query string that we can then later use to actually execute the query. Parsing the query can again go wrong because the query may contain some characters that are not allowed in the GraphQL query language, or it may violate some of the syntactical constraints that the GraphQL query language has, in which case, again, we can abort early and return errors to the client. However, again, let's assume that parsing works. The next thing that we can then do is we can basically validate the abstract syntax tree that the parser created. And validation means basically we check whether within the constraints of the schema that this GraphQL server has defined, right, is this query valid? Does it make sense? So for example, imagine you have a GraphQL server that allows you to query some users, right? And then somebody sends in a query that asks for products, right? It may be that this syntactically is a valid GraphQL query, right? I mean, the parsing will work. It doesn't look wrong. The syntax is correct. But on this GraphQL server, there are no products, right? And so validation will basically catch this and will say, look, on this server, you can't really ask for a product. Products don't exist on this server. The server is really just about users. And so in that case, the validation would fail and an error would be returned. If, however, the validation succeeds, right, then we can go on. Now we enter the GraphQL execution engine, right? So we pass the validated query. And the next thing that we do is we coerce the variable values. So I've shown you what variables are in the slide about the GraphQL query language. So they are basically values that are passed in addition to the actual query. And coercion means basically that there can be slight adaptations of the type. So imagine, for example, that there's a variable that is defined to be a floating point number, right? But the value that the client actually sends is an integer, right? Well, you can translate an integer into a floating point number without losing any information or precision. And so coercion will basically perform this step of translating the types where possible. In some cases, however, of course, coercion is not possible, right? If the variable is supposed to be a number, but you're sending some weird string value, right, then coercion doesn't work. And again, we can abort and send an error to the client. If, however, variable coercion does work, we get into the main step of the execution, which is to evaluate the selection sets, right? So the selection sets contain all these different field selections that we actually want to get data for. And so to evaluate the selection sets, there's some logic which is defined in the GraphQL specification, which is a recursive algorithm that goes through all these possibly nested selection sets and calls the resolver functions that I mentioned on the last slide, at the end of the last slide, right? These resolver functions are implemented, custom implementations by the developer who writes this GraphQL server. And they can basically interact with different other backend systems in order to actually fetch or mutate the data, right? So these resolver functions are being called by the GraphQL execution engine. Some of these are actually called in parallel where possible. In other cases, that's not possible because there may be dependencies, right? You can only resolve a selection set if the parent selection set has already been resolved, for example, right? But if there are selections that are siblings to one another, you may in some cases be able to call the resolver functions for them in parallel, and the GraphQL execution engine is smart enough to figure that out for you. So having called all the resolver functions, the server has now basically fetched all the data that is required to answer that query. And in the last step, it will basically build a response object out of this data and then send it back. So in the previous to last step, right, there was no error returned actually. The last step, however, may contain errors. And this is some interesting aspect of GraphQL, namely that a GraphQL query can be answered only partially in some cases, right? It may, for example, be that we were able to fetch the user data for most users, but not for some of them due to some maybe authentication constraints or something. So the response could, in theory, contain at the same time some partial data of the result and also some error messages. So this is an overview of how query execution on GraphQL typically works. So with that, right, let's turn to some advanced query concepts in GraphQL. So the first one is something that I already mentioned in the beginning of this talk, which is introspection, right? And introspection is this interesting mechanism which allows clients to learn at runtime about the data types and the different operations that a GraphQL server has to offer, right? So it's basically some kind of like programmatic documentation that the client can get from the server. So an introspection query, right? How does it work? An introspection query is actually just a plain old GraphQL query, except that it happens to use some special fields and special types that every GraphQL compliant server has to offer. These are called meta fields and introspection types. And so here on the right-hand side, you see a small example of an introspection query, right? It's a query that's called introspection query, and it makes use of this weird __ schema field, which is a field name that is reserved, so it can only be used by the GraphQL implementation. And then it basically fetches a bunch of information on this schema. And I want to actually give a small demo of this. So let's head back to GitHub, to this API Explorer. And let's write a query that also starts with __ schema. And we can ask this GraphQL server, the one of GitHub, to tell us about all the different types that it has implemented, right? The types that it supports. So we can go for the name of the types and the kind of the types. And we can shoot this query. And what we get back is this long list of types where we have all these objects with the name and the kind. And we can see here from scrolling down that, holy smokes, there's a lot of them, right? This is a really big and complex GraphQL API. So let's maybe focus on something more specific. Let's go for an individual type. If you remember in the example that I gave in the beginning, right, we were interested in pull requests. So there was a type called pull requests. So we can get again the name and the kind. Let's just make sure that this works. Right, so here we have get information about the type pull request that is defined on the GitHub API. You can also get a description maybe. Yep, a repository pull request. And this being an object type, right, we can see if what fields it actually defines. So let's go for the fields and let's go for the name of the fields. So we see, oh, it defines a bunch of fields actually, like active log reason, additions, assignees, author, and so on and so forth, right? And we can say, well, what's the type of these reasons, right? Of these fields, and we can see active log reason, for example, is an enum type, and the additions is a non-null type. So maybe let's also get the description for these fields, right? So we see here, for example, author, right, is an interface type, and the field basically contains the actor who authored the comment, right? So this is very interesting. And if we turn our attention to the right-hand side of this tool, right, we see this documentation explorer. And the documentation explorer basically documents the type system of this API, and it has a search function. We can go for pull request here, right? And we can actually look at the pull request type, and we can look at the fields. And what we notice here is that, you know, the information that is rendered here on the right-hand side is actually the same information that we got here by performing this introspection query here on the left-hand side. So we see that really this tool itself basically uses introspection to fetch information that it can then use to render this documentation for the user, right? So introspection is really an interesting concept because it's queries like any other queries. They just happen to use these special fields and types, and they really allow you at runtime to get some very interesting information about the type system of this API. Right, and just to finish up the slide, so client tools like GraphQL, like you just saw, right, they can really rely on introspection for a bunch of things, right? As you just saw, they can use it to show documentation about the types and the operations. They can also use it for client-side query validation, right? So if we go to GraphQL and if we write some query, put some field in here that doesn't exist, right? You see there's squiggly lines and it gives me an error, right? Cannot query field Eric on type __ type. Well, that makes sense because it doesn't exist. And so the client can basically tell us that there's something wrong with this query without even having to send it to the server. So this is really great. It can also do auto completion. You saw that before when I was forming the queries, right? I typically just started writing the name of some field and then it already suggested to me what that full field name could be, and I could just hit enter. And so there's a bunch of capabilities that introspection enables. So that's a really powerful feature. I've shown you the demo. So the next concept I want to talk about is pagination, right? So pagination aims to return different parts or so-called slices of long lists of data, right? Imagine you have your backend server has a list of friends, right? And you want to only look at a certain amount of them because maybe some user has thousands of friends, right? It's not economic to basically load 1,000 of friends in one go, right? So you want to maybe start with the latest 10 friends that you made and only fetch the next sets of friends as the user goes along, maybe as they scroll down the application or something like that. That's what you typically want to use pagination for. And given the focus of GraphQL for building client application, right, pagination is actually a really important feature. So one way that pagination works is by using slicing arguments in an offset. So slicing arguments are basically used to define the length of the part of the list that you want to return. And the offset basically tells you where to start, right? If you don't provide an offset, you basically just get the front end of the list. And if you put an offset, you can basically shift that slide as a slice that you want to return back. So here's an example query, right? We want to fetch the second page of friends of a user, right? So we ask for a user, we want to maybe get the name of the user, and then we want to get some friends. And the slicing argument here is called last. So we want to get the latest 5 friends, and we want to have an offset of 5. And this is why the query is called fetch page 2, because if we didn't provide the offset, we would get just the 5 latest friends. And here we get the friends 10 to 5, basically, right? And we want to get the name of those friends. So think of it like this, right? This is the list of friends from 1 to 17. The first page would be friends number 13 to 17, and the second page would be friends 8 to 12, right? And by basically defining this offset to be 5, we can now fetch the second page. So this is one way to do pagination. However, this way of pagination has some issues. One problem in particular is that this approach may return items twice when there's list updates. So imagine a changed list, right? So you still have page 1 and page 2, but just before you're about to go to page 2, there's actually these 3 new entries here, right? You made some new friends number 18, 19, and 20, right? So they just became your friends, and now you are performing this query for fetch page 2, right? Your offset is still at 5. So what that means now is that basically when you get this data, friends number 13, 14, and 15 are actually returned twice, right? Because the offset basically got affected by the addition to the list. So that's not ideal. So there's a different way to do pagination in GraphQL, which is a common convention that is especially frequently used by commercial GraphQL APIs, and that's called cursor connections. So cursor connections are this pattern basically where fields that also have slicing arguments instead of just returning the list of friends, they would return a connection object, a single connection object. And that connection object has fields for page info, which I will come to in a minute, and edges. And edges is actually a list of edges, and each edge has a cursor and a node. And the cursor can be used for pagination, and the node actually contains the actual user, which is the friend that you were actually interested in. So this is a slightly more complex way of doing pagination. And as you can see, the query itself also becomes more complex, right? We have again a query called fetch page 2, which goes for a user and the name of that user. And then we go for friends, and we want the latest 5 friends. But here, instead of using an offset, we say after, and then we put in a cursor value, right? So this actually would be typically some kind of UUID, right? And what we get back here is this connections object, which has the page info, which has a field called has next page. So this is really cool if you want to basically render in the UI a next button or not, right? If you have reached the end of your friends list, then you don't want to have this next button, and so you can use the value of has next page in order to decide whether to render that button or not. And then we get the edges, and this is actually going to be a list of edges, and each edge has a cursor, and that cursor can, in subsequent queries, be used in the after argument here, right? To basically define the starting point from which we want to fetch the next 5 users. And then with the node, we actually get the actual user returned, and we once more get the name of that friend. So this approach is robust to list updates outside of the slicing during pagination. So think of this scenario again, right? We have again this list of friends that just updated as we got friends 18, 19, and 20. But the cursor in this case, right, in contrast to the offset, it actually wasn't affected by this update, right? The cursor still points to friend number 13. So even if there's new friends in the list, we can still get the proper second page without having to look at the same 3 friends again. So, and when you think about this feature, which may sound a little bit complex, but has great functionality, right? You have to think again of the use case that it comes from, which is typically Facebook's newsfeed, right? When you scroll through the newsfeed of Facebook, right? That's a constantly updating thing, right? As your friends and your connections, they all add new content to that newsfeeds as you're scrolling down, and the Facebook app is fetching then the next set of news items, right? You don't want to see news items again and again as the list is updated while you're looking at it, right? So this is really, again, there's a specific reason for why this cursor connections pattern was introduced and is now commonly used in GraphQL. So let's talk a little bit about some pros and cons of GraphQL, right? I hope I've conveyed to you that there's a bunch of benefits for using GraphQL for the clients, right? And I'm going to display them based on the GraphQL tool here once more, right? We have instant documentation of the type system built in, right? This is based on introspection, right? We have static typing, which means we have autocomplete and validation. Again, clients can benefit from that based on the introspection feature. We have very predictable responses, right? We have fewer round trips. I demonstrated that in the beginning with the example app, right? Instead of 12 requests, we only had to perform a single request. And we have no overfetching, right? Because the client can really define on a very detailed level what is the data that they want to get. There's a lot of benefits for clients. If we look at the provider side, there's some benefits as well, right? So first of all, one benefit is that you have very happy API consumers, right? Because GraphQL really grants a lot of flexibility and control to the clients, and that's something that they're going to be happy about, right? If they want to change some feature in the front end that they are building, they don't necessarily have to ask the backend team to implement a new endpoint to get that data, but they can simply adopt their queries to do so. You have simplified maintenance, right? You can serve all of these diverse and possibly ever evolving clients with a single endpoint, right? Which accepts GraphQL queries within the constraints that as the backend provider you outline. And of course, you have the self-documentation of the types and operations, which is always in sync with your implementation, and so you don't need to worry that there's something getting out of sync. You have improved performance and operations by allowing clients to fetch only the data that they want, right? You basically avoid having to load, cache, or expose unneeded data that the client may actually not be interested in, right? So this basically reduces the amount of work that you have to do in the backend. And if you look at the queries that your clients are sending you, you can actually really understand what the requirements of these clients are and how they use the data. You can do that on a per field level, which can grant you really interesting insights. And you have the ability to compose heterogeneous backend resources, right? So this picture implies this, right? Your backend systems might consist of different types of databases. They might call external APIs, right? There may be all kinds of legacy systems, and GraphQL is really a nice way to abstract all of these into a unified and easy to use API. So there's a bunch of benefits in there. On the other hand, you have to see that there are some challenges when it comes to using GraphQL, and I want to focus on two in this talk. The first one is HTTP caching, right, of GraphQL requests. So why is this difficult? So there's all different kinds of ways where you can cache requests to an API typically, right? You can cache on the client side. You can cache in the network. This is typically done by proxy caches, which are operated by internet service providers to reduce latency and network load. There can be gateway caches by the provider where they basically intercept requests to the server before they actually hit the server. And if they happen to have the return value in cache, then they can just return it without having to produce load for the server. And then there can be application caches in the server. So there's a bunch of different places. And some of these places arguably are a little bit more difficult to use with GraphQL, right? So specifically, GraphQL often uses HTTP post to send queries. And they could also use GET, but if you want to send a very long GraphQL query, if you use GET, right, you have to encode that query in the URL parameter of the URL, and typically there are actually limits to the length of these URLs. So if your query is very long, then that doesn't work. And so what you do instead is you basically put the query in the payload of a post request, which can be as large as you want it to be, and you just send the post request. Now, in HTTP, post requests are actually not supposed to be safe or idempotent, right? They're not safe, meaning they typically have side effects, right? They change some state. And they are not idempotent, meaning that if you execute them multiple times, right, then each time the state of the server or the resource that you get back will be different, right? And so because HTTP post requests are typically non-safe and non-idempotent, like default cachings in the proxy or gateway layer, right, they typically don't work on post requests. So there you have the first issue, right? The second issue is that HTTP caching typically relies on HTTP headers that define the caching behavior, right? One of them is cache control, which basically says for how long a certain value produced by a server can be considered to be fresh, so it doesn't have to be refetched, so a cache can be used. Or a last modified header, which basically states what's the date when this resource was last modified, right? So these headers are typically used for HTTP caching. And in an API model like GraphQL, where the client has a lot of control over the shape and the size of resources, setting these headers can be really difficult, right? Because it's not just a single user resource, for example, that a server returns, but a query could ask for a user resource in combination with some other resources, right? And so in that case, what's the value of the cache control and last modified headers, right? It could be that it's the worst value of all the resources that are combined by a query, but even figuring that out can be difficult. So what I'm basically saying is that default caching mechanisms that are typically working well with HTTP don't necessarily work well with GraphQL. There are, however, alternatives, right? So one of them is to cache persisted queries. So persisted queries is basically where you take a GraphQL query and you take some other contextual information like the user who sent that query, the client ID maybe, right? And you maybe create a hash out of it and you use that hash as the cache key. And then you can basically come back to a state where you can use default caching mechanisms because the client has no longer sent the actual large GraphQL query in a GET request, but they can just send the small hash key in order to get the response. And in those cases, right, then the proxy or gateway cache can basically just return the cached value based on that hash. Other alternatives for GraphQL caching includes client-side caching using some ID fields that are defined per type, for example. And there can also be application caches typically in the server, right? So the resolver functions that are actually responsible for producing the data to resolve the query, they could actually employ some caching, right? So that they reduce the number of database lookups, for example, that they have to perform in order to return some data. So caching is does not work necessarily as well as other API models based on HTTP do, but there are ways to implement caching with GraphQL. Another challenge is rate limiting and threat prevention, right? So rate limiting and threat prevention is really about the provider basically putting constraints on how an API can be used, right? So they may be interested to do that so that no single client can basically overly use an API, which could be costly, right? Or use it even to an extent where maybe they bring the server down, right? So especially if you're offering a public API, right, which is open to be used by anybody, right? You want to make sure that you have some control mechanisms so that this API is not being misused in some way. And in API models where the backend developers or the provider basically defines the different endpoints, right, they can typically implement very simple rate limiting solutions, for example. They can say, oh, there's an endpoint that returns a user object, right? Well, I'm just going to implement a policy where each client can only call that endpoint 1,000 times per hour, right? And if they try to call it more often, then they're actually going to get blocked, right? So the difficulty with the GraphQL request is that the question of what the implications of a GraphQL query are lies really in the query itself, right? So consider this example query here, right? Called fetch all the data, right? So this query asks for 1,000 users, right? And then for every one of these 1,000 users, it asks for 1,000 orders, right? And then for each of these orders, it asks for the payment details and the status of those payment details, right? That's a very small looking query, but imagine that the resolver function that produces the payment details value calls an external API, right? Which may actually be costly, right? Which may not be free for the backend provider who implements this GraphQL server. So in the worst case, this could be 1,000 users times 1,000 orders. This could be 1 million requests to an external API, right? That could be really problematic, right? This single request, the single GraphQL query could be the equivalent of thousands of REST requests, right? So in GraphQL, it doesn't suffice to say every client can send 5 queries per hour, right? Because the query could be very harmless and simple, or it could be something like this, right, which is really possibly malicious. And so how can you deal with that if you are a provider of a GraphQL API? So there are some different options. One of them is to time out the processing of the request, right? So if the query execution on the server takes more than 10 seconds, right, you just abort basically. That's one option to deal with it. It's simple to implement, but it's not ideal because imagine this query, right? Within the first 10 seconds, maybe you have already called this external API 5,000 times, right? And that may have already induced a bunch of costs. So timeout may be a little bit too simplistic. Another option is dynamic analysis. Dynamic analysis basically means that as you process this query, right, as you execute it, you sum up some values, for example. You sum up, for example, how many users are being asked for. And then if you reach a certain threshold, you basically abort at that point, right? It's a little bit more fine granular control than a timeout, but it still has this issue that you already started to process a query, right? It already may have caused some issues before you actually abort it. So that's also not ideal. The third option is to do static analysis. So static analysis basically is an approach where you try to look at this query or any incoming query and you try to figure out what it does and if it could potentially be harmful before you actually start executing it, right? And there's different ways that you can go about this. One is you can look, for example, at the depth or the nesting, right? So you can see how far nested is this query. And if it's too far deep down, then it's likely that there's a lot of multiplication effects on the line and you may abort it. But then again, if you look at this query, right, it's actually not that nested. It has like a few nesting levels here, and it's still possibly very malicious. So another way that you can go about static analysis is to look at the cost or the complexity of the query. And in this case, that could be, for example, a measure for cost and complexity could be the number of times that the payment details field is invoked, right? And by looking at this query, you can basically figure out, well, 1,000 users times 1,000 orders, you can predict basically that this field, payment details, will get called up to 1 million times, and that's your cost or complexity value. And you may actually then basically have a policy in place that says, look, if the complexity is above 500, then we don't even execute that query. We return an error to the client. Still, rate limiting and threat prevention, right? That's a challenge that you have to deal with if you're building GraphQL APIs. So with that, I actually want to wrap up this guest lecture, right? A summary, I wanted to give you a little bit of background of what GraphQL is and where it comes from. And I think the important thing to remember is that GraphQL really was created by Facebook to address some very specific problems, right? Often with technologies, with new technologies especially, right, you have people reacting in very different ways to them, right? Some people are super excited about every piece of new technology, and they may adopt it without critically asking, you know, do I actually benefit from using that technology? And on the other hand, you often have advocates of the previous iteration of technologies, right? And they may be like, well, this new technology, you know, it doesn't actually bring something new to the table. All the things that it's trying to do, we could already do with our existing technology, and they can easily become very dismissive. And so there's different ways to look at these types of new technology. And with GraphQL, I just want to convey that there's very specific use cases, right? It's not only Facebook, Netflix faced the same thing, SoundCloud faced the same problem, right? That led to the invention of GraphQL. So there are some very specific reasons why GraphQL exists. However, that also means that GraphQL may or may not be beneficial for you to use, right? Really, it comes down to asking, when you ask yourself, should I use GraphQL for building my API? You have to ask yourself some more questions, right? Like, who are the API clients, right? Are they mostly internal client or external clients, or maybe both, right? If it's only internal clients, then maybe threat prevention and rate limiting is not that important, because you can trust the other members of your company or organizations to just send queries that, you know, won't bring your backend down. But if it's an external API that's public to everyone, right, then maybe you need to think more carefully about threat prevention. How is an API being used, right? How will the use of the API or the API itself likely evolve over time, right? So these are all questions that you may want to ask yourself if you're considering to use GraphQL. And with such questions, as is also typical in technologies, right, there's a bunch of trade-offs to consider, right? GraphQL gives you a bunch of cool features and capabilities, but they make some other things that in other technologies are easier to use harder, right? And so you basically have to look at the trade-offs and see what's more important to you. How do you prioritize these different features, right? And the last thing that I want to tell you is, of course, that there's much more to learn about GraphQL than what I have talked about today, right? I briefly mentioned that there, next to querying data, you can also mutate data or subscribe to data, right? There's all kinds of interesting tooling to auto-generate GraphQL APIs that sit on top of existing other types of APIs or on top of databases. There's things called schema stitching and federation, where you basically try to combine the GraphQL schemas of multiple backends into one, and so much more. And so in order to give you at least the opportunity to look into some of these, I have gathered here some additional resources, including some web resources like the official GraphQL website and the specification, some libraries, right, that you may want to be interested in to get started with GraphQL. And also some videos, right? There's a GraphQL documentary, which I recently found out. It's like half an hour video. It's not really a documentary. I think it's more like fan fiction, but it could be interesting to get an overview and to get more insight into why Facebook created GraphQL, and it features interviews with the creators of GraphQL. So it's kind of interesting. And then this second video is also, I actually highly recommend that to you. Zero to GraphQL in 30 minutes by Stephen Lusher, I think his name is pronounced. He used to work at Facebook when this video was created, and he basically, within this 30-minute long video, he built 3 GraphQL backends in 3 programming languages, I think without making any typing error while live coding, right? It's really impressive. And it really shows how you can quickly get started with building a GraphQL backend. And there's also some research papers and books. Some of these were created by myself also. So if you want to get some more scientific insight into GraphQL, then there are some other resources for you as well. And with that, thank you very much for your attention. And yeah, if there's questions, I'm happy to answer them.
Thank you very much, Eric. Fantastic lecture. I learned a lot about GraphQL. That's very nice.
Great.
To everyone, if you do have any questions, either ask them in the question section. We got some already that we want to answer. If you want to speak up, then I will look at the hands up. So please put your hands up if you want to ask a question by audio. But let's maybe start with the question. Oh, so there's a question from Thomas Rausch. Let's open it up for Thomas.
Hi, Thomas.
Hi, Eric. Good to see you again.
Yeah, good to see you.
Thomas from the Distributed Systems Group. So sorry for interrupting your online questions. But you talked about some aspects of GraphQL backend design, like that you need to implement these resolver functions and that there are challenges with HTTP caching, things like that. So are there any other noteworthy considerations I need to take when I implement a GraphQL backend compared to a classic REST API? So for example, because the client can run complex queries in one round trip, when I implement resolver functions that aggregate data from multiple sources, it seems that the backend now needs to do more work aggregating data efficiently. And similar to that, I assume that mutations are a bit different than that of REST verbs that mutate resources. And to expand on that, what tips would you give someone who wants to restructure their backend that uses REST into one that uses GraphQL?
Yeah, it's a great but also very open-ended question, right? I think so. I would really start by carefully considering what of the benefits that GraphQL can bring, right, are relevant for me in that context, right? So I've heard of use cases in my professional context, right, where people were intrigued to use GraphQL, and then you ask them for the type of application and the type of clients, and you figure out, you know, it's an internal application that has basically 1 or 2 clients, right, which are barely evolving over time. And in those cases, right, you can really say, well, you can just use endpoints, right, REST endpoints maybe, and you will basically get the same result as if you were to use GraphQL, because even if somebody sends you a GraphQL query, if that query is never going to change, or if there's not different clients using that API, then there's no benefit for you. So I think answering that question really critically before you even start using GraphQL, like what does it bring me, is really important. It's with regards to specific techniques or recommendations on how to build your resolver functions or how to build your backend. I think it's very hard to say because it's so case specific, right? To remind you, GraphQL is protocol agnostic, right? So there's people who use GraphQL over gRPC, right? Google Remote Procedure Calls or other binary protocols, right? It doesn't have to be HTTP. So the way that GraphQL backends are implemented can differ highly, right? What I've shown in this slide, right, the HTTP example server, that's just one specific way of doing it, but there can be many others. And so I think it's very hard to give a generic answer to your question, to be honest. I think it's very case specific.
All right, thanks.
Okay, there are some more questions. So there was a question earlier on, can servers still be stateless when using cursors?
Can servers still be stateless when using cursors? Yes, they can, because the cursor basically becomes part of the resource. And so you basically just start your slice by a different resource, right? The cursor doesn't need to hold, the cursor is actually sent and maintained by the client, right? So the first request gets a list of 5 friends back. And then the second request, the client basically takes the ID or the cursor value from the previous set of friends and puts it into the next request. So it's the client who maintains the state on where it is in that list, and the server doesn't have to do it. So the server will still be stateless in this case.
Right. Okay, so thank you, Pino, for that question. The next question I have is from Alexander where does the name come from? Why is it called GraphQL?
Yeah, I think I maybe should. That's a good question, because the name is really confusing, and I think I probably should have said that in the slide where I said what is GraphQL, right? It's this query language for networked APIs, right? I think the name comes from the fact that the abstraction of the data model that you have is basically that of a graph, right? You have all these nesting levels that you can do, right? So even if in the backend the data is stored, let's say, in flat files, right? If you create a GraphQL interface where you can create queries that are nested, then you're basically emulating a graph structure on top of that flat data, and that's where the name GraphQL comes from. Now, what's the problem with that name? A lot of people, when they hear GraphQL, they think of graph databases, right? Graph databases are a special type of database where the data is stored in graph structures, and graph databases are great for a certain type of graph traversal queries, right? But graph databases have nothing to do with GraphQL. You could, in theory, build a GraphQL server where the data is in the backend stored in some graph database. That's possible, but it's not mandatory. You can also build a GraphQL API where the data is stored in a relational database or a document store.
I even think that the relational model is more amenable to what GraphQL currently abstracts, right? Where you have the relationships between, the subqueries, sort of. And I also think what is missing for it to be sort of a graph abstraction is transitive closure. I don't think that there's a possibility of transitive closure within GraphQL.
No, I don't think so. Yeah. But you could have, so one of the things that makes it a little bit more easy to imagine how it is a graph is you can have cyclic dependencies, right? So am I still sharing my screen?
Yes.
Okay. Maybe let me give a small example, right? So let's say we get a topic, let's say testing, right? And then, oops. So this is again using the GitHub API, right? So topic, that field, right? It returns a topic, right? And the topic has related topics, and they return topics as well, right? So we can say related topics, and then we can say related topics, and we can go ad infinitum with this, right? We can go on and on.
Got it. Yep.
I mean, I don't know what is an actual topic in this.
Right, but that's because in that case you have a self-reference within topics.
You have a self-reference, right? And so I'm giving this example because it kind of, when you think of a graph, right, you think of node and edges, right? And cycles are something that can exist in a graph, right? And here you have this relationship where you basically have this cyclic relationship. Because you have to write the query, right, and the query matches the structure of the response, you cannot go ad infinitum in this query, right? Every nesting level that you want this query to have, you have to explicitly write out, right? But it's still a cyclic query, basically, right? It goes for topics, related topics, and so on and so forth. So that's maybe an example of how the graph structure can look like, right? And it doesn't matter where the topics are stored, right? The topics could be, there could be a, GitHub could have a flat list of topics with some relations, right? And then GraphQL, the abstraction of GraphQL makes it look like a graph.
Right. Okay, so we have one more question here from Maximilian. So did I get it right that you can't insert data with GraphQL and have to use another API model for the use case? I think no. Then the question is, are mutations used for this use case? And I think the answer to that is yes.
Yeah. You got it right. So you basically, you did answer your first question with your second question correctly. Yes, you would use a mutation. The way that would work, right, is you have these arguments in these queries, right? And the values of these arguments that we've seen so far in my examples, right, they have always been like very simple things, like an individual string, right? But even if we look at, actually, if we look at the GraphQL API, the GitHub API, right, you see that it does support mutations here, right, in the documentation explorer. So what are some of these mutations, right? Add comment, right? Add comment. So you can actually mutation, add comment, and then you have to provide some input. And now the input is, if we want to add a comment, is actually an add comment input. So this is a complex thing, right, where you have to define a subject ID and a body, right? So the input has to be subject ID, I don't know, some ID value, and what was the other one? Body, right? A comment. And then what comes back from this is you basically have to select something from the return value as well. And now you basically have defined a mutation that will add a comment. I can try to run this, but it obviously won't work, right? So it produces data, but it's null. And then it has a bunch of errors in here, right? Not found. Because I'm trying to add a comment to something with a global ID 123, which obviously doesn't exist in GitHub's API. But in theory, I hope you get the idea of how this would work, right? So the input to this argument, right? This could be an arbitrarily complex thing, right? You could have lists of things, you can have complex objects that you're sending. These are all input values that you can send, and you typically send them when you perform a mutation.
Okay, so I see two more questions. Do you have some pointers to efficiency measures, speed, scale, etc.? And most importantly, how much time does it take to process the data to be served via GraphQL? That's an interesting question.
Yeah, it's a good question. So with regards to performance, right? I mean, there's different things to consider. So there could be the performance of the GraphQL execution engine itself, right? And I would argue the performance overhead of that is really negligible typically, right? You're probably in a request going to lose much more time for the network transfer and for maybe doing some database lookups than you're going to lose in the GraphQL implementation that is running all these resolver functions. And so then the discussion about performance should actually not be just about, you know, executing the query, but also how much performance is gained, for example, by sending less data over the wire, right? In my opening example, right, we reduced the number of requests from 12 to 1, right, to get the same amount of, to get the same data that we wanted and to get less of the data that we didn't want, right? And that's a huge performance gain, especially in a mobile context. And when it comes to these different requests that are opened and closed, right? I mean, consider also these are HTTPS requests, right? They do things like TLS handshakes and stuff like that, right? There's a bunch of overhead per request that you basically get rid of if you can basically bundle all of these requests together. When it comes to processing complex queries, of course, you know, if you write a complex query at some point, you're gonna have a performance issue, right? I mean, maybe I can go back here, right? Look at this query, right? Related topics. I mean, I execute this query and you see it spins and spins and spins. You know, as I add more nesting, right, this query is going to get longer and longer, right? And eventually it might even time out if it go further and further in doing this. But then the question is, are these the type of query that you actually build a GraphQL backend for, right? Probably not, right? Because that query doesn't actually make a lot of sense. And so it's very hard to give like an absolute answer. Like you can't really say GraphQL is faster or slower than another paradigm, right? It really depends on the use of GraphQL, right? How is it used?
Okay. So I have maybe one or two questions before we close. If there are any more questions, please post them or put your hands up. So I have one specific question and one that is more open-ended. So you showed us the directive definitions early in this schema or query. I don't quite remember where it was. I think in the query, right?
It was in the query, yeah.
Yeah. So those are sort of hints to the backend as to some of the things that you want, right? The uppercase example.
Yeah, they are pinned to the backend. So you would basically learn about what directives the backend supports when you do introspection.
Okay,
right?
So the backend supports.
Yeah. So to give you an example of introspection, maybe this is one thing that I can quickly show once more, right?
And my concrete question was more on some sort of, what sort of directive definitions have you seen out there? So what are those we use for?
Yeah, okay, so there is, let's start with that, right? So there is 3 built-in directive definitions that are basically specified in GraphQL. One is include, and I've shown this example in the slide on the query. The other one is the opposite of include, which is called skip. So it does the exact opposite, right? So if the value of the if argument of skip is true, then you skip that part of the query, right? And then the third one is deprecated, right? And deprecated is basically used to communicate change. So I think the pull request type right? If we look at the fields down here, right? If we scroll all the way down, then it has deprecated fields, right? So deprecated fields. And so there's a field called timeline, which is deprecated, and there's a deprecation reason. So timeline will be removed, and so on and so forth. And the way that you would basically use that in a schema is, if we go to the schema definition, right? You would basically say, for example, status at deprecated, and then reason, and you say it's old, something like that, right? And so this is a directive that is built into GraphQL. That's a standard directive, and that's basically interpreted by tooling like here to communicate that a certain field or type maybe will cease to exist at a certain point in time. Does that answer your question?
Yeah, it
so
does.
3 directives, right? Skip, include, and deprecate. And the other ones are typically defined by the server themselves.
Right. So then a couple more questions here. Florian asks, yes, we do have less requests, but our query request is much larger than the GET request from a REST API. Where's the benefit?
Yeah, the query is larger than the GET request, but in comparison to the overhead, it's probably much smaller, right? I mean, if you think about, again, my example here, right? I think we went from 34 kilobytes or something to 12 or something. The query that we did send is under a kilobyte. So there's the benefit is still there.
I think also the benefit is, as you pointed out multiple times, just removing those round trip requests.
Yeah.
Just establishing the TCP connection, sending data, encrypting, receiving responses. I think having all those 12 requests is definitely much more expensive than having one request. However, if you see for your use case that the query that you're sending is much larger than the maybe 5 requests you're sending, for instance, then there's a trade-off that you can make, right? I guess. Yep.
So okay, so finally the GitHub API is running faster again, right? So let's look at this, right? So we have again 12 requests, right? This for GraphQL, GraphQL.js, which is the reference implementation. We transmitted compressed 32.7 kilobytes, and it took overall around 2 seconds, right? Let's compare. GraphQL, GraphQL.js, oops, same library. Let's clean this out first. Under 450 milliseconds, oops. Single request, 1.9 kilobytes. That's huge. I mean, if you have an optimized system, right? If your income as Facebook or as GitHub depends on the performance and the user experience of your mobile application, you probably going to be happy if you get a 10% reduction in the payloads that your server sent, right? This is order of magnitude, right? Obviously, this is a little bit of a contrived example, but I mean, there's no argument that this is so much more efficient.
So we have a couple more questions here. Kabula asks, how does GraphQL solve the problem of data interoperability if we perform query federation?
Yeah, that's. I don't think it inherently solves this problem, but I think it gives you a framework on how to build it, right? The way that you would, if you do something like schema federation, where you basically have different backends that all expose GraphQL. Schema federation basically allows you to annotate these schemas so that they can be collectively combined to form a single schema, right? And so that queries to that single schema can be resolved against different backends, right? It doesn't solve some of the hard questions that you're going to have, right? If you have a request coming into your backend system and that request is going to get executed on a bunch of distributed nodes, there is some inherent problems to that GraphQL won't solve for you, right? There is the issue that there may be, network partitioning. Some of these nodes may crash. There's in general latency as you invoke the network in order to fetch all the data. GraphQL won't solve that for you, but GraphQL gives you as an application developer a nice framework to basically build these type of systems from an API and semantic point of view. But then ensuring that the non-functionalities are there, right? That's on a deeper systems level. GraphQL won't solve that problem for you.
Right. So maybe the next question is also interesting and a bit more general by Solomon. Which framework can you recommend? I'm guessing for implementing a backend in GraphQL. Is there anything that seems to be an ad hoc standard or?
Yeah, I think so. There's Apollo GraphQL. I think it's apollographql.com. So Apollo is this, by now actually I think it's a company that's basically evolving around everything GraphQL, right? They have a bunch of different, that's pretty small. They have a bunch of different products, a whole platform basically. So they have libraries for building servers in TypeScript, I think, and client tooling, and the tools that they build are generally very well thought out, and I think you should get started with them. I typically just use the reference implementation, which is a little bit rougher to use. It's not as abstracted, but it still gets the job done. And then you have other options, right? If you really want to minimize the amount of code that you write, I'm going to plug this here, right? This is a project where I'm one of the authors, right? This is a library out of IBM that takes as input the description of a REST API, a so-called Open API document, and it basically translates that into a GraphQL server without you having to write any code, right? So if you have an existing REST API and you have a description for that API, an Open API document, you can basically ingest it into this tool and you get a GraphQL server out of it for free. Nice. And tools like that exist. I also have some in the slides, right? There's a bunch of tooling which basically creates GraphQL servers in front of databases, right? So if you have a Postgres database, there's a tool, PostgreFile, I think it's called, which basically generates a GraphQL server that allows you to send GraphQL queries that then get translated into mutations or database lookups in Postgres. And again, you can really avoid having to write a bunch of code on your own. So look into nice. Apollo, and if you want to write your own, and if you don't want to write your own, then check out the type of open source tooling that exists to give you a GraphQL server without you having to do a lot of work.
Cool. So Simon has a question here. So are the built-in directives picked up by the GraphQL middleware, while the custom directives are processed by the execution engine? Or can custom directives also manipulate the query before executing it, like the include and skip directive?
Typically directives are actually considered during the query execution. So the GraphQL middleware that I've shown you, right? The validation step will make sure that the directives that you use in your query, that they have been defined by the server and that you use them in the valid places and you provide the required arguments of the required type. But other than that, the GraphQL middleware doesn't know anything about directives and typically doesn't do anything with directives. It's the execution engine that then performs some logic based on these directives. Of course, you could imagine you could write a GraphQL middleware, right, which is smart enough to do something about these directives, but typically that's left to the GraphQL execution engine.
Right. Okay. So we have the last two questions now. Reza asks, is OData an equivalent to GraphQL?
Isn't OData semantic annotations for, I'm not 100% sure what OData exactly is, but I think it's semantic annotations for typically used in JSON. Maybe he knows more and he can provide some context. I don't think it's an exact alternative. I mentioned before, right, that Netflix had the same problem at a similar time that Facebook had, and they created this thing called Falcor. And Falcor is basically a direct competitor, you could imagine, right? With Falcor, basically creating virtual JSON resources, right? That you can then, so the client is basically defining virtual JSON resources. So it's actually pretty much the same thing, but different language. I mean, it's different wording used to describe it and different implementation, right? And I think Falcor is just not that actively maintained as far as I know. I don't know. Is it? Well, there are some commits in January. But I think GraphQL has basically gotten more attention and has managed to build a larger community around it, which always helps.
Okay, so then we have the last question by Philip. Should an endpoint use a query field to only fetch necessary data from a database to reduce database processing power usage, or instead fetch all data and let the GraphQL middleware filter it for us?
I think if you can, you want to make your database query as compact as possible, right? So if your GraphQL query only goes for very specific fields, right, then maybe you can translate it into a database query that also only fetches those fields, because otherwise you're losing some of the benefits, right? So if you think of an SQL query, right, you do select and then the names of the fields from and then the table, right? So if you implement it well, you can basically say, oh, somebody wants some user data and they only want the name and the age. So then you can say, you can translate that into a select name, comma, age from user table, right? And then the database query is going to be more compact. You're going to use less bandwidth if you send it maybe over the network. And so I think you want to try to make sure that your database lookups are really also as slim as possible, and don't just let the GraphQL engine and handle that for it. The GraphQL execution engine will do that, right? You could just fetch the whole user document with 50 fields, and then the GraphQL engine, based on the GraphQL query, will filter it down to name and age, right? But that's inefficient, right? I mean, look, if you start building a system, right, you don't want to prematurely optimize it, right? So you might want to start with just fetching the whole user and let GraphQL figure out the rest. But eventually, you know, if that system is used in production, if you have a lot of users, you want to optimize it.
Right, makes sense. All right, and so with that, I think we had our last question. And I want to close this guest lecture. Eric, again, thank you so much. I think it was a fantastic lecture, as evidenced by the many questions that we had. And hopefully next year you can give it in person and come to Vienna.
Yeah, that sounds great. So thanks everybody for listening and for asking these thoughtful questions. And yeah, Jürgen, thank you for inviting me.
Of course.
Maybe at some point in person.
Okay, sounds good. Okay, bye-bye.
Bye.